Well, in this lesson we're going to talk about arc length and curvature. Recall in the xy plane, r squared, that the arc length of a smooth plane curve, if it's given parametrically, is the square root of x prime of t squared plus y prime of t squared dt, t going from A to B. That's from Cap 2. When the curve is described parametrically, okay, and A is less than or equal to t, less than or equal to b. If we use a vector valued function, r of t equals x of ti plus y of tj instead, we could write s equals, this is really the same thing as this, because it's saying the length of r prime of t dt. So the integrand is the length of r prime of t, where r equals this vector value function, or actually this is the three-dimensional version. If we're in 3 dimensions, it would be that. So recall when we developed this, it was based on the Pythagorean theorem, but in 3-dimensional space in our cube, the diagonal of a box would alter this to what we see in theorem 12.6. And here's what we see in 12.6. I'm sure you'll find this a great one to cheer about. And so a smooth curve given by r of t equals x of ti plus y of tj plus z of tk, this one, on the interval AB, if that's the case, smooth is important. That way it's differentiable everywhere. Then the arc length of curve C on that interval is square root of, this is actually just the distance formula, in a way applied to the diagonal of a box. And so it's the usual thing, it's the length, the integral between A and B of the length of r prime of t dt, which is another way of saying it's the integral of the velocity vector. So here's an example. Find the arc length of a helix on 0, pi over 2, and sketch if possible. Note, that's really not really possible except for with software or something like what I'm using here. So I'll show you a picture of it, and then we'll find the length of it. Here's the picture of it. This piece right here. Okay. 0 to pi over 2. I believe this is the y-axis. Here's the x-axis. Here's the z-axis. But for me to graph it, I need to define functions x, y, and z, and so I really am kind of graphing it parametrically, if you will. So we want to find the arc length on 0 to pi over 2 for this function, so what I need to do is integrate between 0 and pi over 2 r prime. R prime is 4 I plus, actually minus 3 sine of t j, and then plus 3 cosine of t k, but the length of that r is the square root of 4 squared. This is actually negative 3 sine of t, the quantity squared, so 9 sine squared of t, and then this 9 cosine squared of t. This might be a little far-fetched for you to see, but I hope it's not. This is 16, this is 9, this part of it is 9 times 1. 9 times 1 is 9, plus this 16 is 25, square root of 25. So when we integrate square root of 25, that's just 5, so we get 5t. T goes from 0 to pi over 2, so our answer, 5 pi over 2, is the length of this curve here. That's approximately I guess 5 pi over 2 is about 15 over 2. It's a little bit more than 7.5, and that seems like a reasonable estimate.